Let's move on to talk about velocity. So when we talk about a wave moving, right, there are two types of velocity that we can investigate. First is we can look at how fast is the wave moving. In this case, how fast is the wave traveling to the right. That's the first type of velocity that you can investigate. The second type of velocity that you can investigate is focus on a specific particle at a specific position. In this case, I focus on this particle at x equals to 2 meter, and I investigate how fast is the particle moving. So in this case, it's moving downwards. Then after that, you continue to move upwards, downwards, upwards in a SHM motion. So we can study how fast is the particle at a specific moment. We can study how fast is the particle at a specific displacement from the equilibrium. So it's similar to SHM if we are talking about the speed of the particle at a specific position. Okay, so this is how fast is the particle moving or how fast is the wave moving. So there are two types of velocity that we can investigate. If we are talking about how fast is the wave moving, then we are talking about wave propagation velocity. How fast is the wave propagating, or how fast is the wave moving, in this case to the right. If you are talking about how fast is the particle moving, we know that all these particles here are undergoing simple harmonic motion. So you can think of this kind of motion as a vibration. So you can call this kind of velocity as particle vibrational velocity. As you can see, the symbol for wave propagation velocity and particle vibrational velocity are slightly different. If you're talking about wave propagation velocity, there is no subscript y. But when we talk about particle vibrational velocity, there's a subscript y. The subscript y here is indicating that this v here, this velocity here, we are talking about the y component of velocity of the particle. So the y component is of course the vibrational direction. So we're looking at the component of velocity of the particle that is in the direction of the vibration. Okay, so these are two types of velocity. We'll go through them one by one. Let's focus on wave propagation velocity. So we know that it's trying to describe how fast is the wave moving. And we know from SPM that the equation is V equals to F lambda. This one you might learn from your secondary school. So let's try to understand properly what does V equals to F lambda means. So we know that F here, it's frequency. So frequency means how many complete wave cycles can you complete within 1 second. If it's 5 Hertz, that means you finish 5 complete wave cycles. Okay. For lambda over here, it's wavelength. So we know that lambda is the distance covered by 1 complete wave cycle. So if you measure the distance covered by 1 wave cycle, that distance will be the wavelength itself. So these two things, why does it become, why when you multiply these two variable here, you obtain your speed. Okay, how will you obtain your wave propagation velocity when you multiply these two things together? Let's try to investigate it. Let's say today I give you an example here in which the frequency is 5 Hertz, the wavelength is 2 meter. Then from there you multiply, you get your wave propagation velocity to be 10 meter per second. So let's try to visualize this situation here using a diagram. So if you sub 5 into the frequency, that means you can complete 5 complete wave cycles within 1 second. Frequency equals to 5 Hertz means that you can complete 5 wave cycles within 1 second. That's the meaning of the frequency 5 Hertz. 5 complete wave cycles within 1 second. Next, so 5 wave cycles means in 1 second, you'll be able to observe that the wave has traveled by this much wave cycle. 1, 2, 3, 4, 5. As you can see here, 1, 2, 3, 4, 5. So there are 5 wave cycles that you are able to see traveling to the, in this case, right, made by the progressive wave. This is what the frequency tells you. Next, if you look at the wavelength tells you that it's 2 meter. Then what does that mean? That it's for one complete wave cycle, the distance is 2 meter. So therefore, you should expect there are 5 times of 2 meters over here. So what is the total distance covered by these 5 wave cycles here? It's 10 meter. So in 1 second, you're able to cover 10 meter of distance. So you cover 10 meter of distance per second. So that is what? That is just wave propagation velocity. That means for every second that has passed, you see the wave travels by 10 meter, in this case to the right. Okay, so every time you start your timer, then 1 second has passed, you see the wave. If you focus on one point of the wave, you see that let's say the crest, you see the crest has already moved by 10 meter within 1 second. That's the idea of wave propagation velocity. You see one specific point, you track it, then within 1 second you see that particle at that shape, that crest here, you can see the pattern has moved by 10 meter within 1 second. That's the idea of wave propagation velocity. Next, we move on to talk about another equation that we can use to get wave propagation velocity. How do we do that? We know that our equation for displacement usually express the time parameters in terms of omega and express the space parameter in terms of wave number. So if omega and k are the usual parameters that you have, then it's probably less convenient to use f lambda. Probably if you re-express this equation in terms of omega and wave number, then the equation can be more useful. So let's try to do that. We know that frequency is related to omega through omega equals to 2 pi f. So frequency is just equals to omega divided by 2 pi. Omega divided by 2 pi, you get frequency. For lambda, you know it's related to wave number. K will be equals to 2 pi over lambda. So lambda is equals to 2 pi over k. Okay, so now we have re-expressed frequency in terms of angular frequency. We have re-expressed wavelength in terms of wave number. So now we can just cross out the 2 pi, one on the numerator, one in the denominator, and we get the new equation for wave propagation velocity, which is v is equals to angular frequency divided by the wave number. So if you want to see how fast is the wave moving, you can also take the angular frequency divided by the wave number of the wave. Okay, so that is another equation that you can use to find the wave propagation velocity. Next, let's move on to another kind of velocity, which is particle vibrational velocity, v subscript y. So for this situation here, we are focusing on a specific particle and try to see how fast is that particle moving. We know that the particle can only move up and down like this in a simple harmonic motion kind of motion. So we will be studying it like how we study it in chapter 9. Okay, so we know that this particle is undergoing SHM, thus we can use some of the equation that we have derived from our chapter 9. So in chapter 9, we learned that if our displacement x is equals to a sine omega t, then we can determine the velocity by differentiating this equation against time. So if we do dx over dt, we'll get equation for velocity at the x component of velocity technically. So the x component of velocity is equals to a omega cosine omega t. Again, you differentiate sine, you get cos, then you have to differentiate inside the bracket, therefore you get this omega. This is what you learned in chapter 9, and you know that there are many versions. There's a cos omega t as well, there's negative a sine omega t as well, there's negative a cos omega t as well. So if your displacement equation is different, then if you differentiate, you get different equation for velocity. It depends on what is your displacement equation. So that's chapter 9. So if you move on to chapter 10, displacement is no longer x. Displacement is now called y. So our equation for displacement is this new equation over here. Okay, so y equals to a sine omega t plus minus kx. So now we have a kx behind. Why do we have kx behind? Because this equation, it's general. It's for all the particles that are along the x-axis here. If you sub in 6 for x, then you are focusing on the particle at x equals 6. If you sub in x equals to 3, then you are focusing on the particle that is located at x equals to 3. You put what number in for x, that means you are focusing on the particle at that position. Okay, so this one, once you substitute in the x, then you focus on one particle already, and the particle you know is undergoing SHM. So you see the equation will come back to the shape of an SHM displacement equation. It's still the same, x equals to a sine omega t plus minus phi. Okay, so this one is if you substitute in x, then you become a sine omega t plus minus phi. Okay, but this is the equation for displacement, and if you differentiate it against time, what we will get is a omega cosine omega t plus minus kx. Again, sine you differentiate, you get cos, and if you differentiate what's inside the bracket here, You are differentiating it against time, so the term behind this is irrelevant. There's no time over here, so you only need to care about the first term. You differentiate omega t, you get omega. That's why you have a omega cosine omega t plus minus kx. Okay, it's still a similar idea as what you learned in chapter 9. So this equation here will describe the velocity of the particle vibrating in this fashion here. Okay, so if you substitute in the x, then you are locating which specific particle you are investigating. So x indicates where is the particle that you're investigating. T will indicate at which moment are you interested with the velocity. Because you know that as the particle here undergoing simple harmonic motion, at different location, at different displacement, the velocity will be different. Let's say if the particle is at the amplitude, then you know that the velocity will be equal to 0 because it's making a U-turn. If you know that the particle is at the equilibrium position, then you expect that the velocity should be maximum. So you know that this is an SHM motion. The velocity will change as the particle moves up and down. So if we specify a single moment, then we are allowed to find the velocity at that particular moment. So that particular moment, the particle can be anywhere. It can be at the equilibrium, or it can be somewhere in between equilibrium and amplitude, or it can be at the amplitude. Depends. Okay, that's why you substitute in the t to know at which moment exactly do you want to find the velocity of the particle vibrating. Okay, so this is the first type of equation that you can use for particle vibrational velocity. But as similar to what I said just now, there's always sine, negative sine, cos, negative cos. So actually you have to be careful. There are many versions of displacement equation. It can be sine, it can be negative sine, it can be cos, it can be negative cos. How do you know it? Look at the position at x equals to 0. If the position at x equals to 0 starts from the equilibrium, then you know it's either sine or negative sine. So how do you track it? You put x equals to 0, then you focus on the particle at the origin. So if the wave is moving to the right, then you trace how would the line looks like if the wave moves to the right. If the wave is moving to the left, then you see how will the line trace at x equals to 0 when the wave moves to the left. Then from there you see whether it traces a negative sign pattern or a sign pattern. Then you know whether it's sine or negative sine. This one I've discussed it in the previous video when we talk about the two different types of graph. Okay, for cos and negative cos is much more easier. If at x equals to 0, your wave starts from the positive maximum displacement, then it's definitely a positive cos. So because no matter your wave travel to the left or travel to the right, your particle will also trace out a cos graph. Okay, if the wave moves to the left, you get a cos graph. If the wave moves to the right, you also get a cos graph if your wave starts from the amplitude over here. Of course, it's the same thing. If you change your wave, the wave starts from the bottom over here. If it starts from a negative maximum displacement, if the wave travels to the left, you will still trace out a negative cos graph. If the wave is traveling to the right, you also trace out a negative cos graph. So cos is easier actually. You see it starts at the positive maximum displacement, then it's positive cos. You see it starts at the negative maximum displacement, then negative cos. But for sine, you have to check how the wave move to the left and move to the right will cause a difference to whether it's a positive sign or negative sign. Okay, so let's move on from there. So we know that this equation here, we can differentiate it against time, then we'll get the particle vibrational velocity. So if you do it, the differentiation yourself, you see that the equation for particle vibrational velocity is different depending on what is your displacement equation. So be careful. This is not a general equation. The main thing that you need to do is to differentiate the displacement equation. And once you differentiate the displacement equation, only you know it looks like what. Okay, so this one is not fixed. It depends on what is your displacement equation. Okay, so this is one way of determining the vibrational velocity of a particle. We specify a location, we specify at which particular moment. So we substitute in the x, we substitute in the t, then we get the particle vibrational velocity. Another way of determining particle vibrational velocity is to say what is the particle's vibrational velocity when the particle it's 0.5 meter away from the equilibrium. When the particle has moved up until here at this point, if the particle has moved up until this point, what is the vibrational velocity? That's another way of asking. Okay, previously I asked which particle at what position, then what time are you interested in? I give you a position, I give you the time, you find me the velocity. Another way of asking is, if the particle has already been displaced 0.5 meter upwards or 0.5 meter downwards, then what is the velocity when it has displaced by this much? That's another way of finding. Okay, we give you the displacement and you find me the particle vibrational velocity. So for that, we have learned in chapter 9 also, there's another formula which looks something like this. The x component of velocity is equals to plus minus omega square root of a square minus x square. So we learn this in SHM. So what we do is, if we have a particle and this particle is it's oscillating around the equilibrium position. So let's say we are interested with the velocity when x is equal to something. So let's say if the displacement is equals to x, what is the velocity? Okay, if I sub in x inside here, what will be the velocity that come out? So that means when my particle has oscillated until this displacement, what will be the velocity? So we are interested with the velocity when the ball reach here. So the ball can reach here in two different ways. It can reach here by moving upwards, or it can reach here by moving downwards. So throughout an oscillation, the ball will pass through this x here either by moving upwards or moving downwards. Therefore, the direction can be both positive direction and negative direction of velocity. That's why you see a positive and a negative sign in front of the equation over here. So whether it's positive or negative, it's both actually. It's never just positive only, it's never just negative only, because you are not specifying a moment. If you are specifying a moment at time equals to 3, then it's a specific moment, then the object must be either moving in this direction or another direction. That is if you lock the time, if you specify the time. But now you are specifying the displacement. So if you are specifying this displacement x here, well, you can arrive at this displacement x here in two different ways. One is by moving upwards from the equilibrium position and reach this point. One is by moving downwards from the maximum displacement and reach this point. So if it's an upward motion, then the velocity will be a positive Vx. If it's downward motion, then it's a negative Vx. So it can be both. It can be positive, it can be negative. That's why your answer have plus minus in front of it. So you cannot just throw away the plus minus like what many students do. You throw away the plus minus. No, you shouldn't, unless they specify the which moment are you interested in, or they specify they want the magnitude or the speed only, and you can remove the plus minus. But now we are talking about velocity, you need to indicate the direction. So if it's so you don't know whether it's upwards or downwards, you just know this point, you don't know upwards or downwards, so you have to include both positive and negative. Okay, so this is what happened in chapter 9. In chapter 10 is a similar situation, just that for displacement in chapter 9 is x, displacement in chapter 10 is y. So what is this equation trying to say? It means that you are trying to find the vibrational velocity of the particle when the particle has displaced by a distance of y. What does it mean? If I displace by a distance of y from the equilibrium position, what will be my velocity? So there are many particles that is having a displacement of y. Over here I draw 7 particles that are at the displacement of y, and all these particles, this equation here allows you to know the velocity of the particle for all these 7 particles over here. Using this equation, you are able to determine the vibrational velocity of all 7 particles over here. Why? Because the magnitude will be the same. Okay, if you're at this height, the magnitude will be the same, but the direction can be different. So let's try to see what happens here. So I'm going to start the wave. I'm going to move the wave by a little. Then I want you to observe how does the particle move, whether it moves upwards or downwards when the wave travels by a little to the left or to the right. Okay, then from there you see that it can be either moving upwards or downwards. So let's focus on these 7 particles. So as you see, if I let my wave travel a little bit to the right, you can see that the particle over here has moved downwards, whereas the particles over here, the second particle has moved upwards. The third particle has moved downwards, whereas the fourth particles have moved upwards. So you can see that all these particles here can either move upwards or downwards, but the magnitude, the speed is the same, just that it's alternating. One is down, one is up, one is down, one is up, one is down, one is up, one is down. Therefore, you still need to keep the plus minus over here, but this calculation here will give you the magnitude. This calculation in front here gives you the magnitude. The plus minus here tells you that the velocity can be either moving downward, like this green arrow over here, or moving upward, the positive one, like this brown arrow over here. So positive indicates the motion is upward, the direction of velocity is in the positive direction. Green arrow here indicates negative Vx, or the direction of velocity is in the negative direction. So you still need to keep the plus minus as usual. Okay, so this is another equation that you can use to determine the particle vibrational velocity. So we have discussed a few equations for particle vibrational velocity. Let's try to summarize them. So you have the particle vibrational velocity equals to dy over dt. So this is the first equation. You take the displacement equation and you differentiate it against time. This equation is used, this equation here, you have to depend on what is your displacement equation. If it's cos, then it's a different equation for the velocity equation. If it's sine, then it's another equation for the vibrational velocity. It depends on what is your displacement equation. The y equals to a sine omega t plus minus kx. So this one is differentiation, the first equation. So this one, if you have the specific moment, you have the specific position, you can use this way of finding the vibrational velocity. The next way of finding the vibrational velocity is to use this equation. But for this equation, you are not specifying any single particle. You are looking at any particles that are at a displacement away from the equilibrium. So if you're looking at all these particles, you should expect that some of the particles are moving downwards, some of the particles are moving upwards. Therefore, there should be a plus minus. Okay, so if they specify a moment, or if they specify a particle at a specific moment, then you should not have plus minus for your answer. Okay, if they specify a moment, a specific particle, then you should not have plus minus because the direction is definite. A particle can only move in one direction at a single moment in time. Therefore, you should have no plus minus. But if this equation is used, that means you are not specifying any particle. You are asking for the velocity of all the particles that achieve the criteria of having displacement of how much away from the equilibrium position. Then there are many particles, therefore some can be moving in positive direction, some can be moving in negative direction. So it's important to know which situation to use which equation. Okay, so it's not suitable to use this equation if the moment in which we are interested in is specified. If the t is specified, use back this equation. Okay, so this is a rough overview for wave propagation velocity and particle vibrational velocity.